In Calculus 1, if we wanted to find the area under the curve y equal f of x from a to b, we drew the picture, we subdivided this randomly into n partitions of unequal width and then created rectangles. When we found the area of each of these rectangles and added them up, that presented a reasonable estimation. If we called this the ith rectangle, then the ith area would be f of xi times delta x sub I. If we added them all up, they gave us a reasonable estimation, but then we wanted to take a limit as the norm of the partition approached 0. Remember, the norm of the partition means the largest such width is approaching 0, because the magnitude in this case would represent widths. And we called this the Riemann sum, and we knew this produced the value of the definite integral. So now suppose that on this ith rectangle, I decide to subdivide it further, and I said, let's divide this particular rectangle into, say, m partitions. And so let's call this one right here, let's call that with delta yj. Then if I said, let's add up all of these, so the sum from j equal 1 to m of delta yj, that would add up to that height of f of xi. Now, let's call this particular rectangle's area delta aij, and then it is clearly delta yj times delta xi. Now, if I said I want to do the same Riemann sum, but I want to do it by adding these up, then what we can do is replace this with this sum. And so what I have is a sum from j equal 1 to m of delta yj, and the sum from I equal 1 to n, and then delta xi, and what this would give me is the sum of every single rectangle if I subdivide all of these into m. So again, starting at, this should be I. Starting at I equal 1, I would add all these up, and that would give me f of x1. Now when I go to I equal 2, I'd add all these up, and that'd give me f of x2, and so on, and so on, and so on. So when I take the limit of this quantity, now the norm of the partition would represent the largest such little rectangle there's area, and we would do a double sum, I equal 1 to n, j equal 1 to m, delta yj, delta xi. Now, this would represent the same area, but in this case here, it would be the sum of the sum, which would mean I want the integral of the integral. So the outer integral is still going to be a to b, but the inner integral will now go from 0 to f of x dy dx with an integrand of 1. Because if I said, let's evaluate this, the antiderivative of this would be y from 0 to f of x, which would then be this quantity. So we've figured out a way to take our single integral and write it as a double integral. This will allow us to segue into 3 dimensions. Now that we know that we can always take an integral and write it as a double integral with an integrand of 1, this is not a very practical approach because we have to work just to get it back to here. But now let's imagine I have a closed region here, some nebulous closed region, and normally we think of taking vertical rectangles of width delta x and then setting it up. But you know from first semester calculus that every area problem can be set up integrating with respect to x or with respect to y, whichever is easier. So I could do vertical or horizontal rectangles. So we generically call this region Rxy, or the region in the xy plane. And then what we do is we say, we want to generically describe this double integral. So we say the double integral over the region, because every region is going to be different, and each region will determine what your limits are going to be, of 1 dA. dA being area, where dA is going to be integrating dy followed by dx, or dx followed by dy, depending on how you want to break up your region. So we sort of generically describe all double integrals that are finding area in this form. Now I want you to think about it a little differently. Imagine that I actually have a three-dimensional shape, but it has a height of 1. So it looks like this, but it's a disk. It comes out 1 unit, and I wanted to find the volume of this thing. Well, obviously the volume of this thing would be the area of this base times a height of 1. So I can look at this as saying, you know, we could think of this as a volume because this allowed me to find the area of the base, and then I multiplied the height by 1. So now the question is, what if the height is not 1? How would we set up that problem? So that's the next step. Now consider that I have a surface, z equals f of xy, but it's finite. And if I project it down onto the xy plane, let's say this is the shadow it creates. That's exactly the term we want to use. This is its projection. And so in the xy plane, this would be rxy. If I wanted to find the volume under this shape, okay, I have a three-dimensional shape with this as its base, then I would set up the integral this way. The integral over the region in the xy plane, but now my height is f of xy, and I'm integrating over the area. Now, again, depending on how the region is defined, I will determine whether I want to integrate with respect to y followed by x or x followed by y. There is no automatic way of doing it, so this is the generic way we set up all problems of this form. So now we can actually try to find a volume in general, so that's what we'll do next. I would like to find the volume where my height is the function z equals 2x plus 2y, and my region in the xy plane is bounded by the lines y equal x, y equal 2x, from x equal 1 to x equal 3, meaning I want this region in here. Now, because I've set it up dy dx, I would be setting it up to do the rectangles in this way. That's the easy part. How do you actually evaluate the double integrals, the part we want to go over first? So what we do is we work inside out. We think of this inner problem first, and we completely solve this problem within the bigger problem. So it looks like this. This will equal the integral from 1 to 3 of. Now I need to integrate this with respect to y. So just like a partial derivative, if I integrate a function with respect to y, then I treat everything that's not y as a constant. So this would be like saying integrate the constant with respect to y, so that would be 2xy. Integrating 2y with respect to y would be y squared, and then I would evaluate this from x to 2x, and then overall I have my dx on the outside. Now, where to put these limits of integration? Well, something that you might want to try at the beginning of a problem to begin with. I know these are the x limits, so it might not be a bad idea for me to write x equals. I know these are the y limits, so it might not be a bad idea to write y equals. Certainly at the beginning that will help remind me where I'm going to substitute them. So both of these are going to go where y is. So in the next step then, when I replace y with 2x, I'll get 4x squared. 2x when I squared is also 4x squared. Now when I replace y with x, I'll get 2x squared. And then here I will also get, or I will just get x squared actually, integrated with respect to x. Now I will simplify this whole mess. So I have 4x squared plus 4x squared minus 2 of them minus another one. That gives me 5x squared dx. Now it's a simple calculus 1 problem. That antiderivative would be 5/3 x cubed from 1 to 3. When I evaluate this, that will be 5/3 times 3 cubed minus 1 cubed. So that would be 130/3. This would represent volume bounded by this. But it's not about the volume, it's actually really about what order do I do things. Now if you check the notes online, I have several examples under double integrals, so make sure you do those and you can understand this thoroughly.